Good evening, everyone. We are in the week 8 problem solving session of the NPTEL course Network Analysis, and week 8 is about graph theory applied to network analysis. Let me share my screen. Are you able to see my screen?
Yes, sir. Yes, sir.
Okay. So till in the last week, we have discussed about multiple theorems and how to use multiple theorems to solve the given network in a much simpler way, which will also save our time. So in week 8, we'll be learning about graph theory and how to apply that to network analysis. So mainly this week mainly is about understanding what is graph theory and how to get the equations for a given network using graph theory. And problem solving session might not take much time. It is completely conceptual. So if you have understood the concept very well, then you'll be able to solve the equations or a given network very simply. So this week I'll be mainly concentrating on the concept, and we'll push the problem solving session towards that. So as there are many concepts that needs to be revised, and maybe you might be not so much confident about. So I'll spend around 75%. So probably around 1.5 hours on the concept and half an hour on the network analysis, like solving network analysis or solving any network using graph theory. So in this week, the problems are or the assignments are based upon how to apply the understood graph theory for any given network. Solving is has not yet come in this week, so probably it might be in the next week. So this week it is all about understanding graph theory and how to write the matrices. There are some matrices involved in it. If you have already gone through the lecture videos, this week lecture videos, you might know. So how to write those matrices for a given network. So for that to be written, we need to have a thorough understanding of graph theory and all the nomenclature, terminology, everything. So which will help us to solve the network using graph theory. So yeah, this week it is all about understanding the graph theory and writing those equations. Solving how to solve all those things probably it will come in the next week. So today it is all about graph theory. Have you gone through the lectures? What Sir has mentioned for week 8? Hello.
Yes, sir, but still it is incomplete.
Okay, okay. Yeah, so I have realized that this is a very important topic, and also it is a bit complicated if you have not understood properly. But if you have understood and have a thorough understanding, then it is very simple. So I'll spend more time on explaining the concepts today, and problem solving will take just 5 minutes to solve each problem if you understand the concept thoroughly. So yeah, don't think about problems currently, but we'll concentrate on the theme. So we'll today completely dedicate for this graph theory, understanding the graph theory. First, let me just give some brief definition of these following terms. So you know network. So network is basically a connection of multiple voltage and current sources and circuit elements. So it is just a connection between multiple sources. Could be voltage source, could be current source, and circuit elements, RLC, all these things. So for a given network, first we'll be drawing a graph. So what is the definition of graph? So graph is basically just a skeleton of the, it's like a skeleton of the network. First we'll understand the definition, then we'll take one example and I will explain what is graph, how to draw graph. Skeleton of a given of a network. And then there is something called directed graph. So graph is just a skeleton, and directed graph is graph including current direction and voltage polarities. So directed graph. A directed graph is a graph voltage polarities. With voltage polarities, like which node is positive, which node is negative, and also current direction in a given branch, how the current is flowing. So if we show that, then it is called directed graph. Now there is another thing called simplified directed graph. So simplified directed graph is just a simplified version of directed graph. Simplified directed graph. Okay. So simplified directed graph is like a directed graph where we are showing all the voltage polarities. I think this is polarities. Voltage polarities and current direction. Here we'll only show current direction and we'll name the branches. So graphs. So this is just a graph with current directions. Current direction and the branches named as a number. Named as a number. Okay, we'll understand this better by considering one example. These are basic definition. Let me consider one quick example that Sir has mentioned in his lecture notes. We'll consider the same example. So let me consider this example. So here we have this circuit. So these are elements. It could be a resistor, capacitor, resistor, inductor, or any other voltage source also. But we are just naming it as or denoting it as a rectangular box for our understanding. But it could be anything. There might be a current source also. So we have connected such thing, and the immediate next thing is we have to consider polarities in a way we want, and also the current direction. So first we'll define current directions. I'll consider the current directions that I have considered in my notes, so that it will be same and uniform throughout the lecture. So this is IE6, and like this is the sixth one, and we here we have IE1, and this is IE4, and then this is IE3. Sorry, this is IE2, and this is IE3, and then this is IE5. So we have assumed the current directions in this way. Now we'll define the voltage polarities. So the current will be flowing from a positive terminal to negative terminal. So this terminal is positive, this terminal is negative, VE6. Similarly, this is positive, this is negative, VE4. Similarly, this is positive, this is negative, VE1. E means element. So either it is the current in that element or voltage across that element. Similarly, this is plus, this is minus, this is VE2. This is plus, this is minus, this is VE3. This is plus, this is minus, this is VE5. Did you understand? So there is a given circuit. We have assumed the currents. The currents I have assumed in this way because all the theory that we'll be discussing today will be based on this polarity. So I have considered the same polarity, whatever Sir has considered. And from the current direction, the voltage polarity has. So until this point, is this clear? Or do you have any doubts?
Clear, sir.
Oh, so this is a network. So it is just a combination or connection of multiple voltage sources and current sources or circuit elements. Here we have considered six elements. We do not know what is inside, but we have considered a network of connection of those six elements. So this is a network. Now, in order to get a graph, first we need to identify the nodes. What is a node? Node is a junction with more than three, like it's a junction with three or more branches. So from here, we can identify this is one node, this is another node, because here three, here also three, and here also three. So let us name this as A node, this is B node, this is C node, and this is O node. O node is like a reference. So now we'll draw graph. So for graph, first we have to draw these nodes. Say this is A, this is B, and this is C, and this is O. Now we'll join them. We'll just join them. So A to B we have one element, and B to C we have one element. So here just one by one mapping. And B to O we have another element, and from here to here we have one element. Here to here we have one element. Sorry. And from A to C, so this is A, B, C, O, and this is our other element. So what we have basically done is we have connected that nodes using these lines. So we have first identified the nodes, then we have placed the nodes. Then each circuit element, like if I use a different color, say AB is AB, BC is BC, AO is AO, OC here is OC, and AC here it is AC. So we are doing one-to-one mapping, and we have considered the nodes and then joined them by the lines. So this is like a skeleton. So we know that there is a connection between A to B, B to C, A to O, B to O, C to O, and also A to C. There are six such branches. So we are drawing the branches for the given nodes for after identifying the nodes. So this is like a skeleton of this network, which also as defined, it is the graph. So graph is like a skeleton of this given network. So this is our graph. Now, what is directed graph? Directed graph is a graph with voltage polarities and current direction. So we'll consider this graph. So let me consider this graph. I'll copy. I'll draw here the directed graph. Okay. Let me erase this quickly. Erase these lines. So this is our graph. Now, what is directed graph? Directed graph is that which has voltage polarities as well as current direction. So individually for each branch, we have to define the current direction as well as voltage polarity. So if I consider A to C, it has current direction from left to right and voltage polarity VE6. So first, let us draw the current polarities, then automatically we can draw the voltage polarity. So IE6 is left to right, okay, and IE4, then IE1. Also, we'll write the names. So this is IE6, and this is IE4, this is IE1, and IE2 is going from bottom to top, IE2, and this was IE3, and this is IE5. So first we have drawn the current directions. Now we'll also mark the voltage polarities. So this is VE6, this is VE4, this is plus minus VE1, and this is plus minus VE2, and here plus minus VE3, here plus minus VE5. So correct me if I made any mistake. So first, for the given network, we have drawn the graph, which is just a skeleton, no direction, no current mentioned, no voltage polarity mentioned. It is just lines connecting the nodes in a given network. It is named as a graph. Now we have mentioned the voltage polarity, also the current direction, which according to our definition is directed graph. So this is our directed graph. So these names are, this terminology you should be understanding and also remembering. So whenever they ask, it will be clear. So this is directed graph with all the polarities, everything. Whereas in the case of simplified directed graph, we will not mention any current uh, names, neither the voltage names, but only current direction and branch named as number. So we'll consider the graph. This is just a graph, right? The graph that we have considered earlier. Okay. So this is the graph. Now, what we'll consider? We'll consider the current direction, but not any name. So IE6, IE4, IE1, then IE3, then IE2, then IE5. So we have considered the current direction. Now comes the naming. Now we are not mentioning IE6, IE2, nothing. We'll just mark any branch as a number. So using the same convention, this is our sixth branch. This is our fourth branch. This is our first branch. This is our second branch. This is our third branch. And this is our fifth branch. So we have considered the graph and we have shown the current directions. We have shown the current direction and we have named each branch as a number. So now I know in the branch one, the current is flowing in this direction. So by default, I know the current is IE1 and voltage polarity A is positive, O is negative, and the voltage is VE1. So we need not give this entire information in the graph itself. The minimum information that is needed is the current direction and the branch number. So we can directly get this graph from this graph. So this is the directed graph. This is the simplified directed graph. So simplified directed graph is graph with current direction and branches named as a number. So this is our simplified directed graph. So until this point, is this clear? The terminology, everything? If you have any question, you may ask. Just the terminology only. We are trying to understand. Is this clear until this point? Hello.
Yes, sir.
Okay. So this is just basic terminology of the graph. Now we'll go to something called tree and co-tree. These are all terminology and these are very much important. So that's why I'm spending time. Tree and co-tree. So first, tree. Tree is a connection between the nodes so that no node is left and no loop is formed. Okay. Let me first write the definition, then I'll explain with the example. Tree is a connection between nodes so that no loop is formed and no node is left. Okay. Let us take a quick example. For the same, let me just erase this. We'll use the same picture throughout our session. So I'll be copy pasting this picture and we'll use it throughout our session today. Someone has mentioned, yes, sir. Okay, I have not checked. Okay, fine. So, sorry, we'll not be using this. We'll be using the simplified directed graph. So let me just copy this because we need the directions also. So simplified directed graph. Okay. So here we have identified 4 nodes. So when there are 4 nodes and we have to connect all the nodes so that no loop is formed and no node is left. So carefully follow. So if I consider this node or this branch as well as this branch as well as this branch, then you can see that I am connecting all the 4 nodes, but no node is left and also no loop is formed. So if I write the same thing here. I will use different color for different notation so that you will understand. When I'm writing green dot, it means the node, and whenever I'm using black color or purple color, it is the branch, and red color is the current direction, and dark green is the branch name. So we'll follow the same thing so that it will be easy for you to understand. So what I have done here, I have considered four nodes, which are the nodes of given graph, and then I'm connecting using these branches so that no node is left and no loop is formed. But there are a number of ways. I can connect AC, then BC, then BO. But this is one example. There are a number of trees that could be possible for a given network. This is one such possibility. So this is called a tree. So now this is what this is called a tree. So this is called a tree. Now, what is a twig? Twig is a branch in a tree. So branch of a tree is called twig. So twig. Twig is what? A branch of a tree. A branch of a tree is called a twig. Right. So here AB is a twig. Sorry, this is O. I forgot to mention. BO is a twig. CO is a twig. So this is a twig. So this branch in a tree is called twig. Okay. So we have understood what is a tree and what is a twig. So now what is cotree? Cotree is cotree are the leftover branches. So here in a tree we have utilized 4 to 5, right? Now 136, the connection of 136 is called cotree. So cotree, what can we say? The branches in the given network which are absent for a given tree. So after drawing the tree, whatever leftover branches are there, those will combine to form a cotree. So here A, B, C, O, right? So let me draw it again. So this is our A, B, C, and O. So this is our A, this is our B, this is our C, this is our O. So what branches are not included here? Branch 1 is not included, branch 3 is not included. And cotree is always mentioned by a dotted line. So you have to mention by a dotted line. BC is not included or BC is included. BC is not included and 6 is also not included. So now this is called a cotree. Now we will mention the current direction. 6 is like this, 3 is like this, 1 is like this. And now we will have 1, 3, 6. Now this is called a cotree. This is called a cotree. You are following, right?
Yes, sir.
Okay. Is the pace too much fast, too much slow, or is it okay? If you feel slow, we can fasten it up. If it is fast, we can slow it.
Sir, it is right.
Hello.
Sir, it is correct.
It is fine. Okay.
Yes.
Okay. Thank you. So this is cotree. Now, what is the branch of cotree called? Branch of cotree is called link. So the branch of a cotree is called link. The branch of a cotree is called link. So here in this case, This BC can be called a link. Okay. Okay. So let us just quickly revise. For a given network, if we consider the connection between nodes, so that node is left and no loop is formed, then that corresponds to a tree. The branch of tree are called twigs, and the branches in the given network which are absent in the given tree, they will form a core tree, and the branch of those core trees are called links. So now these are the definition of this. Now we'll use a variable to represent them. So we use E for number of elements. So number of elements or number of branches in a given network, we'll denote it by the letter E. So here, how many elements are there? Or six branches. So how many elements are there? Six, right? Because in the given circuit, we have six. So we have six. So E is equal to six in this case. So number of nodes. How many nodes are there? Number of nodes. Here in our case, four nodes are there, and N is for nodes. So if four nodes are there, how many elements are needed to connect them? There are four dots. How many lines we need to connect them? Three, right? Because no loop should be formed. So A to B, B to O, O to C. So we need number of nodes minus 1 to connect these nodes. So what is the connection of these nodes? A tree. And what are the branches of tree? Twigs. So how many twigs are there here? 3, right? So the number of twigs are n minus 1. So number of twigs are how many? N minus 1. Because we need n minus 1 lines to connect n nodes, right? So we will be needing n minus 1 twigs. Okay, but also number of twigs, right? This is named by or represented as T. So T is equals to n minus 1. Now, how do we find the number of links? So tree plus co-tree is a given network, right? So in a given network, if there are E number of elements and N corresponds to twigs, then the remaining should correspond to link, because there is no common in between, right? These are complementary to each other. So the number of links, which is also denoted by L, I'm using the red color. So which is also denoted by L, is nothing but number of elements minus number of twigs. So E minus T, which is E plus 1 minus N. So this is the like for any given network, these are the representation. So in this given circuit, how many elements are there? 6. How many nodes are there? 4. So how many twigs will be there in any tree? 3. Because there are 4 nodes, we need 3 lines to connect. Similarly, in a core tree, how many links will be there? Number of elements minus number of twigs is equal to number of links. Or maybe I'll write it here. Number of links is equal to number of elements minus number of twigs. All right. So this completes our basic nomenclature of graph theory. So first we have understood what is graph, what is directed graph, simplified directed graph. Then before we go into analysis, we have understood what is tree, what is core tree, what is branch of a tree, which is twig, and what is link, which is the branch of a core tree. So now with this, we'll go into the graph theory and nodal method. Okay. So first, it's like nodal analysis. So first we'll discuss nodal analysis, then we'll discuss mesh or loop analysis, then we'll go to cut set theory. So for each of them, there are different matrices that we'll be obtaining. So yeah, the time is 6:30. We'll slowly go through and we'll understand all of them. So this week I'll be explaining how to obtain the matrices for a given network, which is also needed for the assignment. In the next week, probably Sir will be discussing how to use these matrices to solve those network. So I'll not be discussing how to solve the network in this week. I'll only be telling you how to get those matrices for a given network, which is actually the main thing, because without getting the matrices, you cannot solve the network. So the main Importance is on how to get those matrices, how to write those matrices. So first part is network analysis. Sorry, nodal analysis. So always we will be considering that given graph. Now here we have drawn tree, here we have drawn co-tree. Both can be drawn in a given network so that we'll know what is the tree, what is the co-tree. So we'll draw that circuit. So our circuit will be like this. So this is A, this is B, this is C, and this is O, right? First we'll draw the tree, then we'll draw the co-tree. So this is 4, 2, and 5. Or if you want to consider another network, say we want to consider another network or another tree, I can also consider 1, 2, and 3. That can also be possible. Like if I consider say 1, 2, 3, this is also a tree, right? This is a connection between nodes so that no node is left and no 1, 2, 3. So this is also a tree because no node is left and all the like no loop is formed. All the nodes are used and all the sorry, no loop is formed. Now we'll write the remaining terms, which is 4, 5, and 6. So we'll represent this by black. This is 4. This is 5. And this is 6. And we'll use red color here. Red color, red color. So this is 4, this is 5, this is 6. So this is 6, this is 4, and this is 5. And our nodes are A, B, and C, right? So this is A, B, C, and O. So we'll use dotted line for code tree and dashed like normal solid line for tree. So that is the thing. So for nodal analysis, we'll do what? We'll apply KCL at each and every node. So we'll apply KCL here, KCL here, KCL here, KCL here. So the convention that we follow is this. Say current is leaving the node. Current is leaving the node. Then what is the convention? We'll consider positive. If the current is leaving the node, then we'll consider positive. If the current is entering the node, then we'll consider it to be negative. All right. So now let us write KCL at node A, KCL at node B, KCL at node C, and KCL at node O. So first we will draw KCL at node A. So can you tell me what will be the equation at node A using this convention? So the currents are IE4, IE1, IE6.
Sir, I1 plus I4 plus I6 is equal to 0.
Yes, yes. So all are positive. So it is IE1 plus IE4 plus IE6 is equals to 0. Similarly, at KCL at node B, what will be the equation? Anyone?
Sir, I3 is equal to I2 plus I4.
Yes. If we want to write a 0 on the right hand side, then it will be minus IE2 plus IE3 minus IE4. So minus IE2 plus IE3 minus IE4 is equals to 0. Now we'll write KCL at node C. What will be the KCL at node C?
Sir, IE3 plus IE6 is equal to IE5.
IE5. But if we want to write 0 on the right hand side, then negative will be for 3 and 6 and positive for 5. So minus IE3. Our basic idea is to write everything on the LHS and RHS should be 0 by. We'll come to that part later. So minus IE3 plus IE5 minus IE6 is equals to 0. Similarly, if I write KCL at node O, then which are positive? IE1 is negative, IE2 is positive, IE5 is negative. So minus entering, right? So positive IE1 minus, sorry, IE1 is entering, so negative, sorry. So minus IE1 plus IE2 minus IE5 is equals to 0, isn't it?
Yes, sir.
Now, if you see the equation at the fourth one can be obtained by adding the 3. If we add these 3, say if we are adding all these 3, so IE4 get cancelled, IE6 get cancelled, and IE3 get cancelled. We will have IE1 minus IE2 plus IE5 or minus IE1 plus IE2 minus IE5. So the fourth equation is redundant equation which can be obtained from the top 3 equations. So we will not consider the third equation. Also, in other terminology, we can say these are independent equations or linearly independent. And this is linearly dependent. Linearly independent. And this one is linearly dependent. So we will not consider the fourth expression, but we'll only be considering the top 3 equations. Now, so now we'll be writing these 3 equations in a format such that it will be like A matrix into IE1, IE2, IE3, IE4, IE5, IE6 is equals to 0. So first, our horizontal line will be elements. So this will be our elements like element 1, element 2, element 3, element 4, element 5, element 6. And vertically down it will be KCL at node A, KCL at node B, node C. So this is node A, this is node B, and this is node C. So for node A, we have IE1, right? So IE1 plus IE4 plus IE6. All the other things will be 0. And for node B, we have minus IE2. So minus 1 and plus IE3. There is less than a minute. So if this meeting and kindly join back, we'll continue our discussion. So plus IE3 minus IE4. Other things are 0. Node C, we have minus IE3 plus IE5 minus IE6. Other things are 0. So now this I'll write as a matrix multiplied by IE1, IE2, IE3, IE4, IE5, IE6 matrix, column matrix given which will give 0, 0, 0. So basically what I have done is I have written this equation in this format. Did you follow how I am writing these things? So first equation is IE1 plus IE4 plus IE6. So if I multiply first row, basically what we have done is we have written this KCL equation in the form of matrix. Okay. So did you understand how we are getting this matrix? Hello.
Yes, sir.
Okay. So this matrix, we are calling it as A matrix. So that our equation will be something like this. A matrix into IE matrix is equals to 0 matrix. Right. So what is the size of A? Size of A. So what is the size of A matrix? Size of A is we have excluded one node, right? So it is n minus 1 cross E, number of elements, right? So how many rows are there? One row is less because we are excluding one node. So because at node O, the KCL is redundant, right? So the KCL here is redundant because it is node O and it can be obtained from these three. So we are excluding one node. So that's why we are getting 3 rows and how many columns? 6 columns. So n minus 1 cross E. And what is equal to n minus 1? Twigs. So T cross E. Like twigs cross E. And what is the size of IE? Size of IE is vertical. It's a column matrix. And how many rows are there? Number of elements. So it is E cross 1. And what is the size of zero matrix? It will be T cross E multiplied by E cross 1. So it is T cross 1. That is the size of this one. So this is how you get a matrix. So how do you get a matrix? By applying KCL at each of the nodes. We will consider one node less because it is redundant. All the nodes are not needed. We will apply KCL at 3 nodes or n minus 1 nodes to be precise, and we'll get the A matrix. Now we'll be using this same thing, and now we'll do node voltages and we'll get the element voltages. So this is one part of nodal analysis. So for each analysis, nodal analysis, mesh analysis, as well as cut set theory, there are two parts. In the first part, we'll get matrix, and the second part, we'll get the transpose of the matrix. So we'll get two equations in each of these analysis. And now we'll be going into expressing the element voltages in terms of node voltages. So here, what are the node voltages? So if I say node, let me use black color. So node voltages, node voltages. So what are the node voltages here? VA, VB, and VC. Assume VO is equals to 0. So VO is our reference. So this I will consider to be grounded. So node voltages are VA, VB, VC. Now we have to express our element voltages in terms of node voltages. What I mean to say is, what is VE1? VE1 is VA minus V0, which is VA. And what is VE2? VE2 is VO minus VB, which is minus VB. So we have to write those equations. Understood? Are you following how to get the element voltages in terms of node voltages? So the heading can be element voltages in terms of node voltages. So we will fix the node voltages because it is nodal analysis. We will fix the node voltages and we will write the element voltages in terms of node voltages. Okay. So if I write VE1, V element 1, what is the VE1? It is VA minus V0 because the polarity will be like this. This is plus, this is minus, right? So VA minus V0. So it will be VA because V0 we have assumed 0. Similarly, what is VE2? VE2 is V0 minus VB. So this will be minus VB. Similarly, what is VE3? Anyone? What is VE4? Can you tell me? What is VE3? Hello. So VE3 is this voltage, and which
Sir,
is this plus, this is
VBO
minus.
minus
Sorry.
VBO sir, VB3 will be equal to VBO minus VCO.
Yes, VBO minus VCO, and since VO is 0, it will be VB minus VC. You are right. So this will be VB minus VC. Similarly, VE4 will be VA minus VB, and VE5 will be VC minus V0, so VC. And VE6 will be VA minus VC. So first we have defined the node voltages, and then we have obtained the the element voltages in terms of node voltages. Now we'll again write this in terms of matrix, where now the elements will be vertically down and node voltages will be in the right side. What I mean to say is nodes will be in this way. So node 1, node 2, node 3, or node A, node B, node C, which is a better terminology. So we'll write node A, node B, node C. And here we'll write element 1, element 2, element 3, up to so on, element 6. So this is element 1, element 2, this is element 3, this is element 4, element 5, and element 6. Okay. So when we say element 1, it is VE1 in terms of VA, VB, VC. So I know here it is VA, VB is 0, or we'll use purple color or magenta. VA is 1, VB, VC is 0. So this is done. And VE2 is minus VB. So 0, minus 1, 0. This is done. Now VB minus VC. VB minus VC. This is done. Now VA minus VB. VA minus VB. This is also done. Now VC 0, 0, 1. This is also done. Now VA minus V6. VC, that is actually, oh sorry, that is VB. VA minus, no, VE6 is, sorry, this is VA minus VC. This is VA minus VC. So we'll have 1, 0, minus 1. Right. And element 4, we have VA minus VB. Element 4, we have VA. Oh, this is also a mistake. Let me VA minus VB. Let me check. So first one is 1, 0, 0, 0 minus 1, 0. The other one is 0, 1 minus 1. This is 1 minus 1, 0. This is 0, 0, 1. This is 1, 0 minus 1. So now the matrix has become something like this. Into VA, VB, VC is equals to V1, V2, V3, V4, VE5, and VE6. So we got something like this. Okay. What we have done, we have considered the element voltages on the RHS side and LHS side a matrix into the node voltages. So this is node voltage, right? This is the node voltage or node voltages, and this is the element voltages. All right. And if you see this one, this will be A transpose. Previously we got A, now it is A transpose. So how do you get A transpose? The first row will be first column, right? So first row is 1, 0, 0, 1, 0, 1. So the first column is 1, 0, 0, 1, 0, 1. Second row will be second column. Second row is 0, minus 1, 1, minus 1, 0, 0. 0, minus 1, 1, minus 1, 0, 0. Third column or third row here is 0, 0, minus 1, 0, 0, minus 1, 0, 1, minus 1, 0, 0, minus 1, 0, 1, minus 1. So this is A matrix into IE is equals to 0. Here A transpose matrix into V node voltages is equals to the element voltages. So we'll get another equation which is something like this. A transpose into node voltages Vn is equals to element voltages Ve. So this is our expression. So for each analysis, we'll be getting two equations. One is matrix into something is equal to 0, and the other one is matrix transpose into something equal to something else. So as a summary of mesh analysis, if I write the summary of mesh analysis, we got two equations. The first equation is A into IE is equals to 0. And the other matrix is A transpose into node voltages is equals to element voltages. So what is the size of A n minus 1 cross E or T cross E, right? So now what will be the matrix size here? E cross T, right? Because it is transpose. Now, what are these VA, VB, VC? These are the node voltages. And how many nodes, how many node voltages we have considered? We have considered one less than the total number of voltages, which is n minus 1. Also, T cross 1. So it is E cross T multiplied by T cross 1, which will give E cross 1. So these are the sizes of the matrices in this equation. So is this clear until this point? Or if you have any doubt, do you want me to summarize again? Okay, let me just quickly summarize nodal analysis. In the nodal analysis, for any analysis, in this case, we have considered one tree, but in this case, it is not needed tree. So we are considering KCL at every node. The current leaving the node is positive, current entering the node is considered to be negative. We have considered the KCL at all the nodes, but one equation is linearly dependent and it is also redundant because it can be obtained from the other equations. So we have not considered that one. Now we have made a matrix expression of that, and then we have understood the matrix sizes. The same thing in for another equation, we have considered the node voltages. We have written the element voltages in terms of node voltages, and then we got the element voltages in terms of node voltages by using another expression. So the mesh analysis summary is A into I equal to 0, A transpose into node voltages equal to element voltages. So this completes our mesh analysis, sorry, nodal analysis. Now we will be going into mesh analysis. So I hope it is clear until this point, or do you have any confusion or any doubts, you may ask me. Do you have any doubt? Okay. So, in the case of mesh analysis or say loop analysis, which is also a word that that can be used for the same purpose. So, in the case of these analysis, in our any circuit, we have considered any loop, but when you are applying graph theory, you cannot consider any loop. We have to consider fundamental loop. So, what is a fundamental loop? So, what is a fundamental loop? So, fundamental loop is if by adding any link to a given tree, a loop is formed, that loop is called fundamental loop. So if any link added to a given tree forms a loop, that loop is called fundamental loop. That loop is called fundamental loop. Okay, let us understand. So we'll consider the previous this graph. So what I mean to say is here we have three links. Now, if I consider say this link, if I consider this link, you can notice that this a loop is formed here, right? Did you understand? If we consider that link, a loop is formed. Similarly, if I consider another loop, say, if we consider this one, say 5. Now, this forms a loop, isn't it? So here one loop is formed. Similarly, if I consider the other link, here other link is 6. So if I consider 6, so if I consider this path, then the tree, inside the tree, this loop is formed with the twigs. So if such scenario appears, then those are called fundamental loops. So here we have fundamental loops obtained when you add a link, which is the branch of a code tree. So when you add any link, if it forms a loop, we call it fundamental loop. As here by adding element 4, it is forming a loop. We'll name it is L4. And here by adding 5, a loop is formed. So L5. Here by adding 6, we are getting a loop. So we'll name it as L6. So is this clear? What is a fundamental loop? Understood? Hello.
Yes, sir.
Oh. So in the case of nodal analysis, we apply KCL. In the case of mesh analysis, we'll apply KVL. In these fundamental loops, you have to remember we'll apply KVL in the fundamental loops. So first we'll apply KVL in loop L4. And what is the convention? The convention is you have like KVL, right? But say VA minus VB or say VA plus VB plus VC is equals to 0. It can also be written as minus VA minus VB minus VC is equals to 0. So you can multiply by -1 and write the equation. But which one is correct way? So here every time the link should have positive coefficient. So here VE4 should be positive. So either we'll go in anti-clockwise direction or we'll go in clockwise direction, right? So VE4 has to be positive. So how will I go? I'll go in anti-clockwise direction. So I'll start from B and I'll complete the loop. Does that make sense? Hello.
Yes, sir.
Yes. So because I want the coefficient of VE4 to be +1, so I'm moving from here to there. So it will be plus VE4 minus VE1 minus VE2 is equals to 0. So is this clear? How we are getting this one? Because I want VE4 to be positive. Or you can write the equation and multiply by -1. Anyway, is fine. But I'm just saying so that you will keep this in mind that VE4, VE5, here VE6 coefficient should be positive. Okay. Now apply KVL in L5. So, and what is the condition? Sorry.
Sir, V4 is positive, but we are taking in anti-clockwise direction.
Yes.
So, sir, how it is, sir? So
Sorry.
in the direction of current, we should take the positive voltages. Sir,
In
in
the
the
direction
direction
of
of current.
no, we are going from VB to VA, right? So like when you are like okay. So when you are going like this. Okay, you mean to say according to our convention, this convention. Or where is our convention? You are saying according to this convention.
Yes, sir.
Yeah, but in this convention, VA is at higher potential, right? Compared to VB. So if we are going from VB to VA, there is an increment in the potential. So it will be plus.
Yes, sir.
So we are going from VB to VA. So there is an increment here. There is a decrement here when you are coming from VA to VO. And from O to B, there is another decrement. So if you go opposite to the direction of current, there is increment in the potential, which is also what we are considering here. So when I'm going opposite to the direction of current, so when I'm going from VB to VA, I am going to a higher potential because VA is at a higher potential. So I am increasing here, going to a higher potential, then going to a lower potential, and then again going to a lower potential. So plus VE4 minus VE1 minus VE2. Understood?
Yes, sir.
Similarly, for L5, we need to consider same as you have pointed out, opposite direction of current. So here also I will consider this way. So I'll start from O, go to C, B, then come back to O. So the equation will be plus VE5 minus or plus VE3 again plus VE2 is equals to 0. Do you agree?
Yes, sir.
Yes. Okay. Now I'll apply KVL in L6. Again, I'll consider the opposite direction of the current in the link 6 because link 6 is forming the loop. So how do I consider? I will consider the current in this direction. So I'll go in this direction. So I'll start from C, go to A, come to O, then B. So the equation will become plus VE6, then minus VE1, then minus VE2, then minus VE3 is equals to 0. Do you agree? I have went from here to here. So there is an increment in the potential, followed by decrement, followed by decrement, followed by decrement. So C to A to O to B, B to C. Got it?
Yes, sir.
Okay. Now again, whatever same thing we have done here, we'll do the same thing. We'll write everything in matrix format. Okay. So first we'll be considering elements. Elements. So the elements are what? 1, 2, 3, 4, 5, and 6. And here are what? Here are loop L4, then loop L5, then loop L6. Okay. So now again we'll write the same expression. So loop L4 we have VE4 minus VE1 minus VE2. Other things are 0. Followed by VE5, VE3, VE2. Other things are 0. Then loop 6, VE6 minus VE1 minus VE2 minus VE3 and other things are 0. So this multiplied by VE1, VE2, VE3, VE4, VE5, VE6. So we'll have VE1, VE2, VE3, VE4, VE5, VE6 multiplied to give 0, 0, 0. Okay, got it? How we are getting the matrix? We are just writing this matrix into element voltages is equals to 0.
Yes, sir.
Now, this matrix is called B matrix. Okay. Now, the good part is what is the size of B? Or let me just first write the equation. The equation, whatever we are getting is B into VE is equals to 0. So we are getting this. Okay. Now, what is the size of B? How do we define? So if you see how many rows are there, the rows are equal to number of links, right? Because we are considering fundamental loops which are dependent on the number of links, right? Hello, do you agree? Hello.
Yes, sir.
Okay. So size of B is number of links cross E, right? So number of rows are equal to number of links and number of columns are equal to number of elements. Also, we know that number of elements, if you go here, number of elements is nothing but number of links plus number of twigs. So E can be written as number of twigs plus number of links, right? E is nothing
Yes,
but
sir.
number of twigs plus number of links. If you closely identify here, in this matrix, we have a unity matrix also, this part. And the size of the unity matrix is L cross L, right? L cross L, because number of rows are L and the other part is E. So if it is L cross L, then how many, what is left here? Whatever is left here, it will be L cross T, right? It will be L cross T, because number of T, E can be written as T plus L. So this is L cross L, this is L cross T, this is L cross E. So usually B matrix can be written as something like this. So B matrix can be written as, inside we have B twigs, then U matrix of links. U is identity matrix. So U is what here? U is the identity matrix. So what we are doing is that we have identified there is a identity matrix in the B having L cross L size. So this is L cross L, this is L cross T. So we are writing this BT, we are writing this as UN because it is an identity matrix. So size of B is L cross E and the size of V is E cross 1. This size is E cross 1, right? So size of VE is E cross 1 and size of 0 is equal to L cross 1. So yeah, this is the first part of mesh analysis. So we have discussed that in each of the analysis, we'll be getting two equations. One is something into matrix into something equal to 0, which we have obtained. Matrix into something equal to 0. And the other equation is matrix transpose into something equal to something else. Now we'll be getting that. So in the case of nodal analysis, we have started with KVL, and in the second part, we did node voltages. Similarly, in the mesh analysis, we started with the KVL. Now we'll go to currents. So, sorry, where are we? I think I have added here. Okay. So in the mesh analysis, we have applied KVL. Now, similar to what we have done here, here we have done element voltages in terms of node voltages. Now we'll be doing element currents in terms of fundamental loop currents. So let me quickly consider this. Where are we? Here. So let me just use the same thing. So we are considering element currents in terms of loop currents. So this will be element currents in terms of loop currents. Loop currents in the sense fundamental loop currents. Okay. So for the loop currents, let us consider this thing. Okay. And yeah, forget about the convention for the time being. Okay. So now we have to consider the loop current and what is the direction of the loop current, whether we'll consider in the clockwise, whether we'll consider in the anti-clockwise. So that is the big thing, right? So the direction, the direction of the loop current, the direction of the loop current should be same as the link current. The link current. So whatever link that is closing the fundamental loop, we should consider the current direction in the same way. So here we'll consider this as the current. Here, we'll consider this as the current. Here, we will consider this as the current. Got it? Got it? Hello.
Yes, sir.
So we'll name these currents as, say this is IL4 because loop 4. This is IL5 because loop 5. And this is IL6 because it is loop 6. Now we'll write the element currents in terms of loop currents. So what currents are passing in element 1? IL4 is passing in this direction and IL6 is also passing in this direction. So IE1 can be written as negative of summation of this and this, right? So we can write IE1 is equals to minus IL4 minus IL6, isn't it? Can we write that? Because the current is going in the opposite direction in both the cases. Do you agree? Do you want me to repeat? If you have any question, you just ask, I can repeat. So if you consider the loop current is going in the opposite direction in the black color as shown over here. So it is going in this direction. So IL4 is going like this and IL6 is also going like this. But IE1 is in the bottom below this direction, right? This is IE1. So my IE1 is minus of this, minus of this. So IE1 is minus IL4 minus IL6. Am I clear? Or are you still having any confusion? Is this clear?
Yes, sir.
Okay. So now IE2. So IE2, if you consider IE2 here downward direction, here upward direction, here again downward direction. So if it is in the opposite direction, we'll give minus. If it is in the same direction, we'll give plus. So IE2 is minus IL1 plus IL2, sorry, IL4, this is 4, IL5 minus IL6 because IL5 is in the same direction, other two are in the opposite direction. Similarly, IL3, if you see, IL3 has two components. One is this one in the same direction, the other one is this one in the opposite direction. So it will be IL5 minus IL6. So this is IL5 minus IL6. Now if you go to element 4, element 4 has only one component, which is this component. So element 4 is nothing but IL4. And if you see element 5 also has one component, which is this component, which means IL5. And element 6 also has one component, which is IL6. If you notice, the element current are equal to loop current for the links. So element 4, element 5, element 6 are the links. So for their case, it is just the loop current. Are you able to follow? Hello.
Sir, can you repeat it,
Okay.
please?
Yeah. So first, we have considered the loop currents by closing the loops. And inside the loop, we have to consider the loop current. So that loop current direction will be in a way which will be just same as the direction of the link current. So here L4 is the element 4 is the link, right? So I am considering the inside current as the same direction. And here L5 is going in this direction. So I have considered this direction also in the same way. Here, this is the loop. So I have considered the loop current same as element 6. Now we have to write individual element current because of these loop currents. So if you consider this element 1, so element 1 is like this. So element 1, because of this loop current IL4, it says IL4 current is flowing in this direction. Okay. And similarly, loop 6, it says IL6 is flowing in this direction. Right. So from the loop currents, it says IL4 plus IL6 current is flowing in this direction. But according to my convention, I have considered the current in bottom direction. So I can say that IL4 plus IL6 is flowing in this direction in bottom to top, or minus of IL4 plus IL6 is flowing from top to bottom. So which is what I am getting here. So individually I will see IL4 is going in this black direction. Here there is no loop current because it is outside the loop. And here IL6 is also flowing in this black direction. So IE1 is minus IL4 minus IL6. And IE2, if you see, the loop current is saying in this element IL4 is flowing from top to bottom. In this case, it is saying IL5 is flowing from bottom to top. In this case, it is saying it is flowing from top to bottom because the loop is like this. So here it will be plus, here it is minus, here it is minus. So plus IE5 minus IE4 minus IL6, sorry, IL5, IL4, IL6. Similarly, IE3. IE3 has here, it is outside the loop, so we cannot, no need of this. Here it is in the same direction, here it is in the opposite direction. So IL5 minus IL6. So is that clear, or do you have any doubts?
Yes, sir.
Okay.
No.
So now we'll write the same thing what we have done in the loop, the nodal analysis. Here we'll have node voltages. In present case, we have loop currents. Here we have element voltages. Now we'll have element currents, but we'll write in the same way. So here we'll have horizontally, we have fundamental loops. Which are L4, L5, L6. Vertically, we have elements. So element 1, element 2, and element 3, element 4, element 5, then element 6. Okay. So IE1 has IL4 minus IL4 minus IL6, 0. IE2 has IL4 minus IL4 plus IL1 minus IL6. Element 3 has 0, 1, minus 1. IE4 is 1, 0, 0, or 0, 1, 0, and 0, 0, 1. So if you see, the bottom is the identity matrix because this is B transpose. So B has identity matrix on the right side. So B transpose will have B transpose at the bottom side. So all these things into IL4, IL5, IL6 is equal to our element currents, which is IE1, IE2, IE3, IE4, IE5, IE6. So this we have B transpose. Okay. So the equation can be written as B transpose into I loop currents is equal to I E element currents. So we again got two equations similar to what we got in nodal analysis, or sorry, mesh analysis. So mesh analysis we have A into I equal to 0, A transpose into Vn equal to Ve. Similarly, in the loop analysis, we got two equations. Let me write those two equations. So this is loop analysis. So in the loop analysis, we have B, first of all, B into what we have? B into loop currents. Sorry, B into element voltages. B into VE is equals to 0. So B into VE is equals to 0. And B transpose into loop currents is equal to element currents. So it is just like if you see, it is they are just complementary to each other. In the first case, which is this mesh analysis, we have first applied KVL and we got the expression in terms of element voltages. We got A into V is equals to 0. Then we have in this case, which is the loop analysis, we have done the KVL and we got in terms of VE, or sorry, this is IE, right? This is VE. So here we got in terms of IE. So here we have applied KCL and we got in terms of currents. Here we have applied KVL and we got in terms of voltages. And then in the case of mesh analysis, we have written the element voltages in terms of node voltages and we got element voltages in terms of node voltages. Here we have done element currents in terms of node currents. So here we got loop currents. So element currents in terms of loop currents. So until this point, is this clear? We have discussed about graph theory and how to implement or how to apply it for mesh analysis as well as nodal analysis. So until this point, is this clear? Hello. Or is it a little bit heavy? No answer?
Yes,
Someone
sir,
is-
clear.
Okay, clear. But I also feel that this week is a little bit heavy and there are many things that are there in this week only. So you have to go through and try to understand, and whatever I am solving or writing these equations today, after today's session sometime, you also try to write those equations and try to understand it. And we will be solving problems which will help you understand better, but it is highly recommended you do it by yourself, then you will understand. And conventions are important. In the case of nodal analysis, we have considered current leaving is positive. In the case of mesh analysis, we have considered here these convention, whatever convention, and here the current direction should be same as this element link current. So these conventions are very clear. Should be very clear. So till now we have discussed about nodal analysis as well as mesh analysis. Now there is a method called cut set method. So previously we got A matrix, A transpose matrix, B matrix, B transpose matrix. Now we will get something called Q matrix and Q transpose matrix. So in the case of mesh analysis, we have learned what is loop. Loop can be anything, right? Loop is just a connection between nodes so that when we started the first node, we'll return to the same node and no other node will meet twice. Okay. And fundamental loop is if any link is added to given this thing, then like given tree, if that forms a loop, then that loop is called fundamental loop. Similarly, here we have cut set. What is cut set and what is fundamental cut set? Cut set is a line. So cut set, similarly, like whatever we have defined here, first we'll define and then we'll come back here and we'll understand using equation. So what is cut set? Cut set is a line which breaks the given network into two halves so that each of the half will have at least one node. So cut set is a line that cuts the given network into two halves. So that each half has at least one node. Okay. Now, what is fundamental cut set? Fundamental cut set means if that line passes through a single twig, then it is called fundamental cut set. fundamental cut set. So it is a cut set that passes or which cuts only one twig. A cut set which cuts only one twig. Okay, so this is the definition, but let us try to understand this by considering our equation. So let me just consider this diagram. Okay. Okay, let us consider this diagram. So I'll draw a line which will cut this into two halves. Okay, so I'll consider not exactly two, just two parts. So I'll consider this line. Okay, so now we have divided this network into left side and right side. And on the left side, we have two nodes here and here. On the right side also, we have two nodes here and here. So now this is called cut set because it is breaking the given network into two halves. Not exactly, but just two parts. And each of these parts should have at least one node. Okay, but is this a fundamental cut set? No, because it is cutting this twig as well as this twig. So how can it be a fundamental cut set? So it is just a cut set, but it is not a fundamental cut set. So what is fundamental cut set? Now we'll come back here. So fundamental cut set is that cut set which cuts only one twig. So if I cut it like this, say here I cut like it is a line, but I'm bending it so that we are only cutting this. Or I mean to say, like if I cut it like this, then it is only cutting one twig, right? Instead of writing that line, I'm drawing it like this. And similarly, if I cut it like this, then it is cutting only two. And if I drew like this, it is only cutting three, right? So this is cut set one, this is cut set two, this is cut set three. Do you agree? Are you following? We are just trying to cut one twig. So there are three twigs. So we will get three cut sets. Are you able to follow?
Yes, sir.
Yes. So these are called fundamental cut sets. Fundamental cut sets. And cut sets, how many cut sets will be there? It will be dependent on number of twigs. So if there are three twigs, we'll have three cut sets. If we have n minus one, sorry, if we had t twigs, then we'll have t cut sets. So the number of cut sets is equal to number of twigs. Okay, so number of cut sets or number of fundamental cut sets, not cut sets. Cut sets can be anything. So we have number of fundamental cut sets is equal to number of twigs. Oh, similar to what we have done in nodal analysis, we'll do the same. We'll apply KCL. But how we'll apply KCL here in the same way. So if we consider this node 1, there we have considered one type of convention. There, what convention we have considered? If a node is leaving the current, then it is positive. If if a current is leaving the node, it is positive. If the current is entering the node, it is negative. So here we'll be considering somewhat different. So if the current direction is same as that twig, it is positive, else it is negative. So if current direction in a branch is same as the twig, that implies it is positive, else it is negative. We'll understand by considering the case here. Okay. Okay. So first we'll let me consider this circuit there, so we can easily draw. So we'll consider this here. So we'll again apply KCL at the three nodes, KCL at node A, KCL at node B, KCL at node C. Okay. So first part, KCL at node A. KCL at node A. So the convention is same. If current say at node A, the tweak current is going out. So if the current is going out, it is positive, else it is negative. So all the cases the current is going out, right? So the equation is IE1 plus IE4 plus IE6 is equals to 0. Got it? The convention is according to the tweak. So if the tweak current is going out is positive. If the tweak current is going in is positive. Understood? Hello. Yes, sir. Okay. So at node B, if you consider at node B, the tweak current is entering. So at node B, current entering is positive, current leaving is negative. So IE to IE4 is positive, IE3 is negative. Sorry, actually it will not be at node B, it will be across the cut set. So here in this cut set, there are three currents it is cutting. One is 6, one is 4, one is 1. So I should not say at node A. So I'm sorry. So it is KCL at cut set 1, KCL at cut set 2. So cut set 1, here it is one current, here it is another current, here it is another current. So three currents. Whereas cut set 2, if I use different color, here it is one current, here it is another current, here it is another current, and here it is another current. So it has four currents. And how the convention is like? The convention is according to the tweak. So if the current is entering, then it is positive. So IE2 is positive. So we have IE2 is positive and IE4 is also entering. So plus IE4 and IE6 is also entering. So plus IE6 minus IE5 is equals to 0. So what I mean to say is here the current is like this. Here also the current is like this. Here also the current is like this. But here the current is like this. So all the currents which are in the same direction as the twig will be positive, other will be negative. So only IE5 is in the opposite direction. So IE5 will be negative. Understood? Hello.
Sir, IE6 is leaving, it is not entering.
Which one?
Sir, IL6.
IL6. So you have to consider one side of the cut set. If you are considering the left side of the cut set, you have to consider only this side. So I mean to say, you have to consider only this side of the cut set. So in that side, IE6 is entering. IE4 is also entering. IE2 is also entering. And then IE5 is leaving. Got it? Or you can consider this side. In this side, IE2 is leaving, IE4 is leaving, IE6 is leaving, and IE5 is entering. So either you consider this
Yes,
side
sir.
or you consider that side. But the convention
Yes.
is that weak current should be positive. Other is according to that. Now I'll apply KCL at cut set 3. KCL at cut set 3. So cut set 3 has also similar thing. IE3, IE5, IE6. So IE3 should be positive, right? So IE3 and IE6 are in the same direction. IE5 is in the negative direction. So IE3 plus IE6 minus IE5 is equals to 0. Follow? Like did you?
Yes, sir.
Yes. So now we have to again write in the Q matrix into IE is equals to 0 format. So these will be elements. and here cut set 1, cut set 2, cut set 3. So elements are like 1, 2, 3, 4, 5, 6, right? So if I write IE1, IE4, IE6, 0, 0, 0. IE2, IE4, IE6 minus IE5, 0, 0. Then IE3, IE6 minus IE5 and 0, 0, 0. The entire thing multiplied by IE1, IE2, IE3, IE4, IE5, IE6 is equals to 0, 0, 0. Now, this matrix is called Q matrix. And if you see inside the Q matrix, we have identity matrix here. And the size of the identity matrix will be twigs cross twigs because the number of cut set are equal to number of twigs, right? So the Q matrix size will be T cross E because number of cut sets are equal to number of twigs. And this is E cross 1 and this is T cross 1. So if we write the equation, we will have Q matrix into IE is equals to 0. Also, Q matrix can be written as inside we have twigs identity matrix followed by Q links matrix. So this is called identity matrix. This is identity matrix. So is this part clear or the last part should I explain again? Okay, I'll just quickly explain. So cut set, we have to consider fundamental cut set. So fundamental cut set is it will break the circuit into two parts so that each side there will be one node. And fundamental cut set is cut set which cuts only one twig. So number of fundamental cut set equal to number of twigs. So the convention is same. We have to apply KCL at the cut set one. So we have to apply around this cut set one. So how many branches it is cutting? 6, 4, and 1. So you have to always consider one side of the cut set, either left side or right side. It doesn't matter which side you are considering. So here I have considered say right side of the cut set one. In the right side of the cut set one. So let me say in this right side of the cut set one, I have to find consider the convention that twig current is positive. So if the twig current is leaving, leaving is positive. If the twig current is entering, entering is positive. All of them are leaving. So leave all of them are positive. Similarly, if I consider cut set 2 and if I consider this side of the cut set, you have to see this IE2, IE4, IE6 are having same convention. They are positive. IE5 is having different direction. So it is negative. Okay. So similarly, if you consider cut set 3, I will consider this side of the cut set 3. So IE3 and IE6 are having same convention. So positive. IE5 is having other convention. So negative. Is this part clear how we are getting this KCL at cut set 1? KCL at cut set 2, KCL at cut set 3.
Sir, we have to consider both twig and link.
Yes,
We have
yes,
to
yes.
consider.
So
Yes,
while
sir,
applying
clear.
KCL, you have to consider all the elements, but the convention is current direction of the twig is always positive. If it is leaving, for that cut set, leaving is positive. If it is entering, for that cut set, entering is positive. Because why? Because we need to get a unity matrix here, right? So the twigs are here, 1, 2, 3. So 1, 2, 3 here, 1, 2, 3 should have always positive. Then only you will get unity matrix here. So if you have considered negative minus IE1, minus IE4, minus IE6, here you will get minus 1, which is not the identity matrix. So the convention is that twig coefficient should be always positive. Accordingly, the convention changes for different cut sets. Understood?
Yes, sir.
Okay. So now everything is like the same. First we'll get one Q into I is equals to 0. As we are applying KCL, now we will apply the element voltages in terms of twig voltages. Okay. So whatever copy paste we have done. So now we will do element voltages, expressing element voltages in terms of twig voltages. Element voltages in terms of twig voltages. Sir, when to consider the left side of the cut set and when to consider the right side of the cut set? Yeah, good question. So you can consider any side of the cut set. So let us just consider cut set one. So cut set one, if I consider the left side, what happens? Current one is entering the cut set, right? So current direction is here, here, here. So the convention is current entering the cut set is positive. So all of them are positive. Okay. Now, if I consider the right hand side of the cut set, all the currents are leaving and twig current is also leaving. So current leaving the cut set is positive. Again, all of them are positive. So what actually changes is the convention, but our equation will not change. So you can either consider left hand side or you can consider right hand side, but you have to see that the twig current is always positive. So in one side it may be current entering is positive, then in the other side current leaving will be positive. So it does not matter which side you consider, but the convention that you have to follow is this convention, that the current direction in the branch, if it is same as the twig, then it will be positive, else it will be negative. So maybe your convention changes, but the equation should remain same. So now we are applying the twig voltages or the element voltages in terms of twig voltages. So what we are trying to say is we have VT1. So the convention is this. We will consider VE1 as V twig voltage and VE2 as VT2 and VE3 as VT3. So these are the convention that we are following. Okay, sir. Yeah, thank you. So now these are the convention we are following, and we have to write the element voltages in terms of these twig voltages. Okay. So let me write the table. So our VE1, VE2, VE3, then we have VE4, then we have VE5, then we have VE6. So VE4, VE5, VE6, VE1, VE2, VE3. So we have assumed that the twig voltages are element voltages. Here the twig is AO twig, BO twig, CO twig. So V1 is VT1, V is VT2, then VT3. So this is my VT1, this is my VT2, and this is my VT3. Okay, so now what needs to be done is we have to write VE4, VE5, and VE6 in terms of twig voltages. So what is VE4? Anyone? What is VE4? VE4, say from B, we are going to A. We'll go in this direction and in this direction, right? So it is VT1 plus VT2. Or let me clear it properly. So this is my twig voltage, right? This is plus, this is minus. Here this is plus, this is minus. Here this is plus, this is minus. So VE4 is nothing but this VE2 from here to here plus here to here. So VE4 is VT2 plus VT1, right? Do you agree? We are going in this direction. From B to A. VBO is increment in the potential. VOA is also increment in the potential. Do you agree? Hello.
Yes.
Okay. So our VE4 is VT1 plus VT2. Okay. Now what is my VE5? So for VE5, I need this plus and this minus. So I will go in this direction and then in this direction. So initially there is a decrement in the potential, then there is again decrement in the potential. So it will be minus VT2 minus VT3. Do you agree? because we are going from O to C, because the potential is positive at C.
Yes, sir.
Okay.
Yes, sir.
So this is minus. So the expression is minus VT2 minus VT3. Similarly, for VE6, what we'll have? We'll have VT1 plus VT2 plus VT3. I'll explain why. Because we are going from A to C. And how are we are going? We have to only consider the twig path. So this is one path, this is one path, and this is other path. And for VE6, which is positive, this side is positive, this side is negative. So how are we going from C to B? Increment in the increment in the potential. Then B to O, increment in the potential. Then from O to A, increment in the potential. So from C to A, we have 3 increment in the potential. So the VE6 is VT1 plus VT2 plus VT3. Is this clear? Hello.
Yes, sir.
Okay. So now we'll again write in the same way that we have done in this case. So where the here we are writing the element voltages in terms of node voltages here. Here what is the case? Here it is loop currents, right? So this is here it is loop currents. And this is element currents. Now we'll be writing the element voltages in terms of twig voltages. So here we'll write element voltages in terms of twig voltages. So if I write the matrix, here it will be twig voltages. So we have 3 twigs, twig 1, twig 2, twig 3. And vertically it will be element 1, element 2, element 3. So element 1, element 2, element 3, element 4, element 5, element 6. So we'll write the equation. So first, element 1, element 2, element 3, it will be identity matrix because it is VT1, VT2. So this is 1, 0, 0, 0, 1, 0, 0, 0, 1. Now VE4 is VT1 plus VT2. So VT1 plus VT2. Then VE5 is minus VT2 minus VT3. This is 1, 1, 1. So the entire thing into the twig voltages VT1, VT2, VT3 is equals to the element voltages VE1, VE2, VE3, VE4, VE5, VE6. And if you see, this is Q transpose matrix. We can also check whether we are getting the Q transpose or not. The row will become column, column will become row. So the column here is 1 0 0 1 0 1. 1 0 0 1 0 1. Here the other row is 0 1 0 1 minus 1 1. 0 1 0 1 minus 1 1. This third column is 0 0 1 0 minus 1 1. 0 0 1 0 minus 1 1. So this is Q transpose matrix. And these are twig voltages. And these are element voltages. And if you see, the identity matrix is at the top. Because in the case of Q matrix, it is at the left. Now it will be at the top. And the Q transpose matrix size will be the transpose of this. So this will be, this is T cross E. Now we'll have E cross T. So this is E cross T. And this is T cross 1. So we'll have E cross 1 here. So to write the equation, we can write it as Q transpose into the twig voltages is equal to the element voltages. So in order to summarize the cut set method, if I write as cut set method. First thing is we have Q matrix into I is equals to 0. Then we have Q transpose into twig voltages is equal to element voltages. So every method we'll get two equations. One equation is a matrix into something equal to 0. The other thing is matrix transpose into something equal to something else. So let me take a moment and summarize first the equations that we got. Then I'll summarize what we have discussed. So summary of graph theory. Summary of graph theory. So let me just copy paste the results that we got in all the methods. So first method is mesh analysis. So let me just copy paste. So first one is the mesh analysis. Then we have so first one is nodal analysis. The other one is loop analysis or mesh analysis. So the other one is loop analysis. Last one is cut set method. Cut set method. So these are the equations. So in all three of them, we'll have different things, and the relation between these matrices, the detail of the matrix relation, and how we'll use this to solve a given network. These will be discussing in the next week. So the main aim of this week is to understand the terminology in the graph theory and to understand how to get those equations, what are the different terminologies, and how to get the these matrices A, B, and Q for a given network. So this is the basic objective of today's session. So we have only 5 minutes left, but today I'll be taking another half an hour extra so that we can solve the problems. If you have some work and you cannot continue, you may leave, but as this will be uploaded in the YouTube video, you please go through. But first, now I'll be summarizing what we have discussed today, then we'll go into problem solving session. You will realize that problem solving session is very easy. Only you have to understand the conventions, how to get the matrices and everything. So let me just summarize. First, we have started with the graph theory terminology. Network is just a connection between sources and circuit elements, and graph is the skeleton of network. Then we have understood what is directed graph, what is simplified directed graph by taking one example, and we'll be considering simplified directed graph for our analysis. Then we have understood what is tree. Tree is just a connection between nodes so that no loop is formed and no node is left. And the branch of tree is called twig, and co-tree is the remaining branches that are absent in the given tree. And the branch of co-tree is called link. And then we seen the relation and the variable notation for this terminology. And then we went to nodal analysis. Nodal analysis. First we will do KCL. Then we will do the representation of element voltages in terms of node voltages. So here we have considered this convention. Current leaving is positive, current entering is negative. It is same for all the nodes. All the nodes we follow the same convention. Whereas cut set, the convention is different. You need to take a note of that. So here three equations are independent and the other one is redundant. So we remove that and we consider these three equations form this type of matrix. So we'll get one equation. In the other equation, we assume node voltages VA, VB, VC and write element voltages in terms of node voltages. Then we got another equation. So the summation or the summary of mesh analysis is A matrix into element currents equal to 0. A transpose matrix into node voltages is equal to element voltages. Now we come to mesh analysis where we discussed about fundamental loop. Fundamental loop is if any link is added to given tree, then the loop is formed. So number of fundamental loops are equal to number of links. So here we started with KVL and we got expression in terms of element voltages for the first part. Second part is writing the element currents in terms of loop currents. So here first we have applied KVL and we made sure that VE4, I mean the voltage coefficients of the voltages of the links should be positive because it will lead to identity matrix. So we have considered that convention, and we got the KVL, and then we have written in terms of this matrix, we will get B matrix into V is equals to 0. Then we have written element currents in terms of loop currents. So the loop current should be in the same direction as the link current. Considering that convention, we got element currents in terms of loop currents, and we got this matrix. So first one is B matrix into element voltages is 0. The other one is B transpose matrix into loop current is equal to element current. Then cut set method. Any cut set is which divides the network into two parts, so that each half has at least one node. Whereas fundamental cut set is it will cut only one twig. So number of fundamental cut set is equal to number of twigs. And here the convention is different. Current direction in a branch is positive if it is same as the twig. It is negative if it is the opposite. And you can consider either the left side of the cut set or the right side of the cut set. It is up to you, but only the convention changes. So convention at CS1, if you see, consider the left side, all are entering. So as twig current should be positive, all will be positive. If you consider this cut set 2 and the left side, only 3 are entering, 1 is leaving. So the convention is twig, this is positive, so these 3 are positive, this is negative. Similarly, cut set 3. Then we got this Q matrix, and the equation is Q matrix into element currents is 0. Then we are writing element voltages in terms of twig voltages. In the case of nodal analysis, we did for node voltages because it is nodal. Here it is cut set, and it is dependent on twig voltages. So we have assumed the twig voltages and written other element voltages in terms of these twig voltages, and we got another equation Q transpose into twig voltage is equal to element voltages. So the summary is this: A into I equal to 0, A transpose into VN equal to VE, B into V equal to 0, B transpose into IN equal to IE, Q into I equal to 0, Q transpose into VT equal to VE. So there is less than a minute. If this meeting can kindly join, now we'll solve few problems to get A matrix, B matrix, Q matrix. We'll solve 3 problems. And yeah, if you have any doubts, you can ask. Then we'll go to the problem solving session. So I think we'll continue till 8:30. If you have any doubts, you may ask. Hello. Do you have any doubts?
No, sir. Continue with problems.
Okay. This meeting will end, then we'll start problem solving session. So let this meeting end, then we can start. So if you are free, please attend so that we can discuss, else you can check. So yeah, we'll start the problem solving session. So we'll solve 3 problems, 1 problem for each of the matrix. How to get A matrix, how to get B matrix, how to get Q matrix. So yeah, today's problem solving session. Today it got delayed because the content that needs to be taught is huge, and it is actually mandatory. Without knowing that, there is no point in solving problems because that needs to be very much clear. So problem solving session. So for the problem solving session, you need to be active and you have to answer. I'll only be correlating the theory with the problem solving session, but you need to be attentive and you have to answer it. So first we'll start with A matrix, and also one part I have forgotten that these matrices have a name, and the name is as mentioned here. So I'll mention here. So the A matrix is called. So the A matrix is called a reduced incidence matrix. Reduced incidence matrix. And the B matrix is called fundamental tie set matrix. Fundamental tie set matrix. And then the Q matrix is called fundamental cut set matrix. So these are the names. So they might not ask what is A, but they'll ask what is reduced incidence matrix. So you have to also know these things. So that's why I'm writing it over here. As this will be uploaded, you can refer to these notes. So yeah, the first problem solving session, or sorry, the first problem. So the first problem is shown over here. They are asking what is the fundamental tie set matrix, which is the B matrix. So let me take a screenshot of this and we'll go there. First, I'll ask you a few questions and then we'll go into solving this. Okay, let me copy paste it here. This is too big. Okay, so this is problem 1. And we are calculating fundamental tie set matrix. Fundamental tie set matrix. Okay, fine. First, you tell me how many elements are there? How many? What is the number of elements here?
5,
7.
7.
7.
Yes, 7 are the elements. So elements are the branches. There are 7. And how many nodes are there?
6 nodes.
6 nodes. And how many? They have considered a tree, right? So they have considered 1, 2, this. So all the nodes are connected. There is no loop form. So how many twigs are there?
5.
Yes, 1, 2, 3, 4, 5. So how many links will be there?
2.
2, right? Which is also E minus T, 2. And T is N minus 1. Anyway, it is just the same. So first we are to find the fundamental tie set matrix. So we want to find B. So if you go here, they are asking B matrix directly. So for getting the B matrix, what we will be doing? So B matrix is dependent upon the fundamental loops, right? What is a fundamental loop? Fundamental loop is a loop should be formed if we add one link to a given tree. So here, how many loops are there? Or how many fundamental loops can be formed?
2.
2, because there are 2 links. So I'll correlate the theory versus the math, then you'll understand. So here, what we have done in the mesh analysis or loop analysis to get B matrix, we need to find the fundamental loops. The fundamental loop, number of fundamental loops are number of links. So we have named those fundamental loop by the link that is added. So this is L4, this is L5, this is L6. And within that fundamental loop only, we have applied KVL, right? And from the KVL, we got the matrix from which we got the B matrix. We are going to do the same thing. So what we are going to do is, first we'll let us draw this circuit in a small way. So this is one, this is one, this is one. One thing is they're trying to confuse us with the branches and the node names. So that needs to be we need to be very careful with this. Okay, and these are dot. These are also dot. So my first I'll draw the current direction. So this is my 5, this is my 1, and then this is my 3, this is my 6, and this is my 7, this is my 2, and this is my 4. Okay, I'll write these names, these node names in circle so that those are nodes, and the red color are the branches. So this is my 5th node, this is my 6th node, this is my 2nd node, this is my 3rd node, and this is my 4th node. So I know that number of fundamental loops are equal to number of links. So number of fundamental loops equal to number of links. So there are 2 loops for which I have to apply KVL. So let me just copy paste this. So this is my first loop I'll create here, and this is my second loop that I'll create here. So the first loop is created by considering the first link. So this is one loop. So which is the loop? This is the loop. And it is formed by adding the link 6. So I'll name it as L6. And here I'll combine this. I'll use this link. And this is the outer loop. That is uptime. I'll name it as L7. So that's why if you go to the question, they are considering loop 6 and loop 7, they are asking. Okay. So we'll apply KVL in loop 6. KVL in loop 6 or loop L6. In that L6, KVL in L6. And we have told that that link voltage should be positive while writing the KVL. And we have considered the current direction opposite, or we went in the opposite direction. So current direction is this. So we'll go in this direction. So we'll start at 3, go here, come here, come here. So now can you tell me the KVL expression? Say from 3 we are going to 5, 5 we are going to 6, 6 we are going to 2. So we are basically going in this way. So we have started here, we'll go here, then here, then here, then here. Can you tell me what will be the expression?
V2 plus V3 plus V5 plus V6 is equals to 0.
Not exactly. Okay, so if current direction is this, this is plus, this is minus. If current direction is this is plus, this is minus. If current direction is this is plus, this is minus. If current direction is like this is plus, this is minus. Now you tell me. From 3 to 5, 5 to 6, 6 to 2, 2 to 3. We are starting from here. If you are going to higher potential, it is plus. If you are going to lower potential, it is minus. Can you tell me?
Sir, VL6
Sorry, your voice is not audible properly.
Sir, VL6 minus
VE6, VE6.
VE5. Sir, that is sir, link.
But it is element voltage, right? So even if it is a link, if you go back to theory, we are writing the element voltages and then we'll get a matrix B into element voltage is equal to 0. It may be link, but we are writing the element voltages. So similarly, we'll write here the element voltages. It may be link, but we'll write the element voltages.
Sir, VE6 minus VE5 plus VE3 plus VE2.
VE3 plus VE2 is equals to, yeah, very good. Now we'll write KVL in L7, similar way. KVL. I hope others are also understanding. If you have any issue, you just tell me, I'll explain again. So in L7 also, we'll make sure or we'll go in that direction so that this will be positive. So first let me draw the polarity. This is plus, this is minus. Here this is plus, this is minus. Here this is plus, this is minus. 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 So we are going always from minus to positive in the link. So what is our direction? We'll start from here, we'll go here, we'll come back here, we'll come back here, and we'll go here. So this is the direction that we are going to traverse. So now can someone else tell me what is the equation? So you have to see minus plus, plus minus, plus minus, plus minus, minus plus, plus minus. So first one, minus to plus. So is it plus VE7 or minus VE7?
So plus VE7.
Plus VE7. And then can you continue? What will be the other terms?
Minus VE4,
Okay.
minus VE2, minus VE3 plus minus VE3 plus VE5 minus VE1.
Minus VE1 is equals to 0. So others are following. Did you understand how we got this equation?
Yes.
Okay. So let me just pull this above. This one also a little bit above to make some space. Now we'll write B into V is equals to 0. So in the top row, it will be elements. And here it will be L6, here it will be L7 loop, right? So elements are 1, 2, 3, 4, 5, 6, 7. I am considering circle because we should not consider element with the branches. Or are these branches? These are branches only. So these are not nodes. So I'll write like this only. Then in the first case, VE6 minus VE5 plus VE3 plus VE2, 0, 0, 0. Then VE7, then minus VE4, then minus VE2, then minus VE3 plus VE5 minus VE1, then 0. Are you understanding how I wrote this directly from the equation? Did you follow?
Yes.
Okay. Okay. Into VE1, VE2, VE3, VE4, VE5, VE6, VE7 is equals to 0, 0. So we got our B matrix. So this is our B matrix. Now let us just quickly go back to the theory. I want to show you something. So if we go back to the theory where we have discussed B matrix, we have realized there will be L cross L identity matrix. So we'll check whether we are getting L cross L identity matrix. What is L? 2, right? So we need to get 2 cross 2 identity matrix on the rightmost side. So if you see, we got the identity matrix 2 cross 2, isn't it?
Yes.
Yes. So we'll just go back and see whether the answers are correct or wrong. So we have 0, 1, 1, 0, 0, 1, 1, 0, minus 1, 1, 0, minus 1, 1, 0, and minus 1, minus 1, minus 1, minus 1, 4 minus 1 followed by 1, 0, 1, 4 minus 1 followed by 1, 0, 1. So basically, you just need to have the understanding of how to get the matrix and the convention that needs to be followed. Then you will get the this B matrix simply and you can solve. So is this problem clear or do you want me to explain again? If you have any query, then I'll explain again. If you are clear, then we'll solve another problem. All of you, are you able to understand?
Sir,
Fabian,
explain these
Nidhu?
directions once again.
Okay, okay. So we discussed that like in a loop we can go in anti-clockwise direction or we can go in clockwise direction, but the convention is you have to go in that direction so that this link voltage should be positive. So first I have given minus plus plus minus everything. So if I go from top to bottom, we are going from plus to minus, which means there is a decrement in the voltage, so it will be minus VE6, but I don't want that. I want plus VE6 because it is a link and we want positive. That is the convention. So I have to go from bottom to top. So bottom to top and then covering the entire loop. So here we are going in this direction. Whereas if you come over here, minus is in the top, plus is in the bottom. So we have to come from top to bottom and then cover the entire loop. So so that if you see here, VE6 coefficient is positive, VE7 coefficient is positive, which are responsible for this identity matrix. So that is the convention, which if you follow, you will get the identity matrix. If you do not follow, you will not get the identity matrix. So that is the convention which decides how to traverse. Here, if you see, we are going anti-clockwise. Here, if you see, we are going clockwise. Why? Because VE6 coefficient should be plus 1. Here also VE7 coefficient should be plus 1. Accordingly, only we have to traverse. Is that clear? Or
Yes.
do you want me to explain?
Cleared, sir.
Okay. Okay. Don't be afraid. If you are still having confusion, you ask me, I can explain again. So now we are going to problem 2. So here which matrix we need to find? Hello. In this problem 2, which matrix we are asked to find?
Sir, cut set.
Cut set, yes. So let me just put it here. So fundamental cut set matrix. So let me make it even more small. Okay. So here in the problem 1, we have fundamental tie set matrix. Now this is problem 2. So this is problem 2. We have fundamental cut set matrix. Okay. Before we go into the details of the problem, first tell me how many elements are there, how many nodes are there, how many twigs are there, how many links are there. Any one of you can answer.
Sir,
How
four,
many elements?
four.
4 elements. Good.
4,
Nodes, 4. Twigs,
4, 3,
and 3. And links,
1.
1. Good. So we have this. And now let us quickly go back to our concept. Just correlate the concept. So in the cut set method, we have to find fundamental cut set, and we will consider individual cut set, and we'll apply KCL at each cut set so that the current direction, the convention is in that way so that the twig current is positive. So if it is leaving, then leaving is positive. If it is entering, entering is positive. Then we'll apply KCL and then we get the Q matrix. The same thing we'll do here. So first let me draw the small diagram of this one. So here 1, here 2, here 3, here 4. And this is dotted, this is a line, this is line, this is also line. So this is my 2, this is my 1, this is my 3, this is my 4. And the current direction is, this is 1, this is 2, this is 3, so this has to be 4. So now let me enlarge it. So how many cut set, fundamental cut sets we'll have here?
Sir, 3.
3, because there are 3 twigs. So we'll have to cut it. So let me use some different color, maybe purple color. So we'll have to consider cutting only one twig. So first I'll be considering this one, which is cutting which twig, third twig. So I'll name it cut set 3. And then I'll consider this one, which is cut set 1. And here I'll consider this one, cut set 2. So now let us follow one convention. We will consider,
Sir,
hello.
Sir, it is cutting 2 twigs. Cut set 2.
Oh, sorry. Yeah, you are right. Yeah, thanks for correcting. So this cannot be cut set 2. So the cut set 2 has to be this one. Yeah, thanks for correcting. So this is our cut set 2. Now we'll take different convention, either left side of the cut set or right side of the cut set, and then accordingly we'll solve. So in the cut set method also, we'll apply KCL, right? We'll apply KCL at cut set 1, KCL at cut set 2, KCL at cut set 3. So we'll apply KCL at cut set 1, KCL at cut set 2, KCL at cut set 3. What is the convention? The convention is, if the twig current is entering, then entering is positive. If the twig current is leaving, leaving is positive. So for cut set 1, say we'll consider the left side of the cut set 1. We'll consider only this region. Okay. So this current is like this and this current is like this. So what will be the expression in terms of IE1, IE4? Twig current is positive. So accordingly, the convention is decided.
IE1 minus IE4.
IE1 minus
IE4.
IE4, right?
Yes.
Is equals to 0. So now at cut set 2, also we can consider this region. So here the current direction is like this, here the current direction is like this. So now tell me what is the equation at cut set 2? We are considering this region. So we are considering this region.
Sir, IE2 plus IE4 is
IE2
equal to
plus
0.
IE4 is equals to 0. Yeah, you are right. Others are also following, right? IE2
Yes.
plus IE4. Okay. And the cut set 3, say we'll consider now in the other side. So let me just erase this. So cut set 2, say we are considering this direction or in this region. Now we have the current in this direction here, in this direction here. So only two people are answering. Maybe I'll ask Nia, can you tell me what is the equation for cut set 3 KCL? Both are in this direction. Or you can mention in the chat box also. Okay, if you have any question, you ask me. Or do you have any question? If you can, if you are facing an issue, you can ask me. Or maybe others can you tell what will be the KCL at cut set 3?
Sir, IE3
Minus
plus
IE3 minus IE4
is
Or
is
equal
equal
to,
to
sir, both will be positive and is equal to 0.
yes, both will be positive because our twig current is positive. That is our convention. So twig current entering. So entering is positive. Here also it is entering. So entering is positive. Kavya, is that clear?
Yes, sir. Yes.
So entering it is positive. So it should be the same convention. Maybe for one cut set entering is positive. Maybe for one cut set leaving is positive. But the fundamental thing is twig currents should have positive coefficient. So that is the fundamental thing. So Nia, are you able to understand how we are getting this? Okay. So in the numerator we have elements. In the numerator we have elements. And here we have cut set 1, cut set 2, cut set 3. So elements are 1, 2, 3, 4. So what will be the first row? 1, 0, 0, 1, 1, 0, minus 1, 0. Tell me what will be the values? 1, 0 in terms of IE1, IE4.
1 0 0 minus 1.
Okay. For other lines, here
0 1 0 1.
0, 1, 0, 1. Here
0 0 1 1.
0, 0, 1, 1. Okay. So this is our Q matrix. Okay. Into IE1, IE2, IE3, IE4 is equals to our 0, 0, 0 or 4 zeros, 3 zeros, right? Okay. Before checking, I'll just correlate one concept that we have learned. So in cut set matrix, the first matrix of T cross T, twigs cross twigs, is identity matrix. Okay. Here, how many twigs are there?
3.
3. So identity matrix should be 3 cross 3. As you can see, we have 3 cross 3 identity matrix. Got it. So this is our Q matrix, cut set matrix, Q. Okay. So we'll cross check with the answer. So the answer says, so again you have to see here they're saying cut 1, cut 2, cut 3. We are also writing cut set 1, cut set 2, cut set 3. Because they are cutting that particular twigs, else it will be again wrong. Okay. So our answer is here. What is our answer? 1 0 0 minus 1, 1 0 0 minus 1, 0 1 0 1, 0 1 0 1, 0 0 1 1, 0 0 1 1. So is this part clear? How to get cut set matrix?
Yes, sir.
Okay. Then we'll quickly go to reduced incidence matrix or A matrix. So yeah, this part will be very easy because you have done KVL, KCL, and this is only KCL, right? So this will be very easy, and there is no confusion here. The other two parts, there is some convention that we need to follow. Here the convention is very straightforward. Okay. So this is our problem 3. And here we are trying to find reduced incidence matrix. Reduced incidence matrix. Okay. So first tell me how many number of elements are there? What is the value of E, nodes, twigs,
6 elements.
6, right?
Yes, sir.
And the nodes
4.
4. For getting the A matrix, we are not considering any tree, right? We are applying at all the nodes. So there is no point of twigs and links. If you see B matrix, it depends upon the number of links, right? So we have to mention links. Here it is dependent on number of twigs. So we have to mention the twigs. Whereas a reduced incident matrix, it is dependent on nodes. So there is no point in considering any tree because we are applying at the nodes. So no need to mention twigs, no need to mention links. So tree, co-tree, you need not mention. So that's why they have not mentioned. So here what we'll be doing? So we'll go back to theory, correlate. So in the case of nodal analysis to get A matrix, we'll apply KCL at 3 of the nodes or n minus 1 nodes. And then using that, we'll get the A matrix. So current, if it is leaving the node, then it is positive. If current is entering the node, then it is negative. So let me take this here. And yeah, so the convention is this. And so how do we know at what nodes? So there are 4 nodes. We have to apply KCL at only 3 nodes. So which 3 nodes? That they should give. Node 1, node 2, node 3. So we have to apply KCL here, KCL here, KCL here. So quickly tell me what will be the expression. So KCL at node 1. KCL at node 2. KCL at node 3. So this is the convention that we need to follow. So can you tell me what will be the KCL at node 1?
I1 plus I5.
Sorry, your voice is very low. Can you speak loud?
Sir, I1 plus I5 minus I3 is equal to 0.
Yes, IE1 plus IE5 minus IE3 is equal to 0. Now at node 2,
Sir, I4 minus I2 minus I5 is equal to 0.
yeah, IE4 minus IE2 minus IE5 is equal to 0. Okay, and node 3, this node 3.
Sir, I1 plus I4, IE1 plus IE4 plus IE6 is equal to 0.
So all are positive or negative is there?
All are negative, sir.
All are negative, yes, because current entering is negative. All are entering, so minus IE1 minus IE4 minus IE6 is equals to 0. Okay, so this is our convention. According to our convention, we are writing. Now we need to get the A matrix, right? So
Sir,
here
we
we
can,
sorry.
sir, we can't write it as positive. So because it will be
Yes,
equal
no,
to
no,
0.
you cannot write it as positive, because if you write it as positive, when you are considering this matrix or this equation, it is fine because it does not matter if you multiply by +1 or -1. But the convention is violated. That's why we are using a convention, so that we all fall onto the same, uh, like what do I say, same matrix. Else, we are not following any convention, right? Even if you come here, the question is, instead of IE1 minus IE4, I can write minus IE1 plus IE4. If you write that, you will not get identity matrix here. So we are fixing that convention and we are following that convention throughout. So here we are fixing current is leaving the node means positive, current entering the node means negative. So at node 1, this is leaving, so it is positive. This is entering, this is negative, it is leaving, so it is positive. So accordingly, we are following. So at this node also, you have to follow the same convention. Entering, entering, entering. So all are entering, so all are negative. So minus should be there. Else our matrix will not match. So the convention is fixed, you have to follow the convention. Is that clear?
Yes, sir.
Okay. So first we'll write the elements. There are how many elements? 6 elements. So we'll write 1, 2, 3, 4, 5, 6. Then we'll write KCL at node 1, KCL at node 1, KCL at node 2, KCL at node 3. So can you tell me what will be the matrix values? First row. Here 1 or 0.
1 0 minus 1 0 plus 1 0.
0 plus 1 0. Yes, you are right. And the second one? 0 minus 1. And
0 1 minus 1 0.
0 here, 1 0 minus 1 0, right? And the last
Yes,
one?
sir. Minus 1 0 0 minus 1 0 minus 1.
Okay. So this is our A matrix. A matrix will not have any identity matrix inside it, so we will not get anything. So IE2, IE3, IE4, IE5, IE6. So into this entire thing is equals to 0, 0, 0. So this is our A matrix. Now we'll check whether we are getting the right A matrix or not. So 1 0 minus 1 0 1 0 1 0 minus 1 0 1 0 0 minus 1 0 1 minus 1 0 0 minus 1 0 1 minus 1 0 minus 1 double 0 minus 1 0 minus 1 minus 1 double 0 minus 1 0 minus 1. So we are getting it. So this is just a few example, but you can solve a number of example and get a similar type of equations. So just to summarize, first in the problem solving session, we have considered fundamental tie set matrix, which is dependent upon fundamental loops, and number of fundamental loops are equal to number of links. So we have found out the links, and then we have to consider the direction of traverse in such a way so that the link voltages, elements of the or the element voltage of links should be positive. So here it is coming in this direction, here it is coming in this direction, and we have applied KVL, and then we have written in terms of matrix to get B. In the cut set matrix, we know that fundamental cut set matrices are equal to number of nodes. So here we have 3 nodes, sorry, not nodes, the twigs. So there are 3 twigs, and we have defined the cut set. And the convention is in such a way that the current of the element, which is a twig, should be positive. So we are considering IE3, IE1, IE2 be positive, and accordingly we wrote KCL at each of these cut set, and then we written in terms of Q matrix, and it has identity matrix here. It has it has identity matrix here. Now in the case of A matrix, it is just very simple. Current, if it is leaving the node positive, else it is negative. Apply KCL at the nodes that they have specified. Here they could have also specified 134. Then you have to write 134 only. 3 nodes only because one node is redundant. But whether 3 nodes they have specified or not, they should specify. For those 3 nodes only, you have to apply. They have said 1, 2, 3, so we have applied it 1, 2, 3, and then we got the A matrix. So yeah, so this is all about graph theory. So there is so much concept into this. So this week we have only got how to get the matrices, how to get the equations, but how to solve using these matrices and how to solve and what are the relationship between these matrices, all those things we'll be discussing in the next week. Yeah, so that is it for today. If you have any queries, you may ask. I think it is too much. It's almost 2 or 40 minutes. But yeah, it is actually needed so that you'll be able to solve the problems. But if you have any queries, as this video will be uploaded online, you can go through. If you have no more doubts, then we can end this session here. Or if you have any doubts, you can ask. Okay, thank you, sir. Thank you. Thank you for joining and thank you for staying till then and actively answering the questions. Yeah. Okay, then all the best for your assignment and hope this video is helpful. See you in the next week. Bye. Good night.